So anyway, I like to give a lecture on some results related to criticality and Griffiths phases on statistical physics. And I would begin with the introductory sentences. Can you see it now?
Yeah,
First
right.
sentence, one by one. Yeah.
Yeah.
Okay. So there is a hypothesis that there is a criticality in the brain, which is supported both by theory and experiments, that the brain is at a sustained activity just at the edge between active and inactive phase. And the references are provided, the first references are provided there. And another important thing is about the heterogeneities, because I will focus on the effect of heterogeneities in statistical physics models, which are very important for neural networks as they make the brain more efficient. I just borrowed this sentence from another journal, neuron journal. And the third important introductory sentence is that criticality is affected by these heterogeneities in spreading models in case of finite topological dimensions. And this was our results published in PRL in more than 10,000 years ago. So questions will be posed. What is the topological dimension of the available connectome graphs? Are they small word-like? Are they scale-free? And can we find critical dynamics by modeling? Okay. Did you see the second slide already?
Yes.
Okay, fine. So just I provide a little introductory, although I guess most of you are physicists, so it will not be very important about phase transitions and criticality, just by showing this trivial phase transition of the water ice system, where in general you have the first order transition separating the ice from the liquid and the gas. But at the end of the vapor water first ordered line, there is a critical point. And at this critical point, there are very strong fluctuations. And even beyond the critical point, you can go between these two phases, between water and vapor, with a crossover phenomenon. But if you are just at the critical point, you are close, the correlation length diverges, and there is a rescaling invariance, which is also said the system is scale-free, which means if you rescale the distance r by b, all the thermodynamic functions are homogeneously rescaled with the function of b. Z is the dynamical exponent and chi is the some other physical quantity dependent exponent. So, for example, as the consequence of this rescaling, you find power loss in the specific heat defined as usual, or in susceptibility and in autocorrelation functions. Okay, so why do we find criticality in the brain experiment? And this has started long time ago when Bex and Plants published their results in 2003, which were electrode local field potential measurements for humans and animals. You can see on the graphs two examples. One of them is in anesthesia, and another one is in an awake state when electrodes are displaced on the brain, and electrical spontaneous avalanches, avalanche distributions were measured. And you can see in the log-log plot, there seems to be some power law, although the extension of the power law is not very wide. It's hardly 2 decades. But these measurements were repeated in vitro for balanced exhibitory and inhibitory states, and other experiments for fMRI, Bolt signals, voltage imaging, calcium imaging, MEEG, EEG, and long-range temporal correlations, which means some behavioral autocorrelation measurements done by a Finnish group of Palva. And here I just show the results of the LRT3. On the plots, you can see the exponents measured in the task and in the rest states for the lifetime of and for the size, the total spatial temporal size of the avalanches measured, and as a function of some controlling of the measurements, which I don't go into details, you see that these alphas provide some values for the size around 1.5, and for the lifetime somewhat larger, around 2 in both task and rest states. These are a little bit in contradiction with the first experiments by Becks and Plants, who claim strictly mean field values. Here, excuse me, the alpha is denoted by tau, so they claim in Becks and Planks that these are mean field exponents, tau equal 1.5, and tau t for the temporal size is 2. So these are corresponding to the mean field of the simple branching models. So the next question is, why would the brain be critical? And there are some advantages, because due to the criticality and the diverging fluctuations, there is a high sensitivity to stimuli, as it can be shown on the plot. And furthermore, the correlation functions divergence cause optimal transmission and storage, information storage properties for such systems. So you don't need to be 2 neurons hardwired, but due to the long-range correlations, very distant neurons can communicate due to this diverging criticality. Okay, and the most important thing which has been done by some informatic processing studies, that there is a maximum of this capability of such neural systems and in computational performances. But there are some disadvantages of criticality. First of all, you have to tune at the critical point. And the second one is, if you are close to criticality, there is a danger that you fall into the supercritical regime, which is can be considered epilepsy in human behavior. To understand this tuning, self-organization criticality is proposed first, and most of the models use this. And now I just show you a picture which I have taken from Trends of Cognitive Science by Higatak and colleagues, where they consider this criticality dilemma. how can it be achieved? In one way, you have this self-organized criticality, which fine-tunes the system via feedback into the critical point. And another thing is this Griffith phase phenomena, which I will speak about, where instead of having a single critical point, you have an extended phase. So you don't need to tune so precisely at the critical point, but even below the critical point, you can find dynamical scaling behavior. Some comments. SOC and Griffiths phase do not exclude each other, so they can live together in certain models. And for SOC, you really need a responsible feedback mechanism, which is in statistical physics usually is a competition of slow driving and a fast dissipation. But Griffiths phase can occur spontaneously in heterogeneous systems. And we expect that the brain is really heterogeneous. So let me move on towards the simplest statistical physics model, which I will consider. These are some threshold models where the nodes, which are indexed by the index I, can be in states of inactive or active one. Later you can extend it with more states like refractory states and so on. But inactive state can become active if the weighted sum of the activity of the neighbors exceeds some threshold value denoted by K. And in our model, we accept this activation with some probability lambda. So in a graph, you have this I, and you have the neighbors I2, IC, whatever. And an active site can become inactive with spontaneously, but with probability mu. Usually, we select mu equal lambda minus 1 to decrease the number of independent control parameters. The other parameter in this system is the density of active size rho. And these systems can be considered as reaction diffusion models, where M active sites are needed to come together in order to achieve an activation. So M active sites become M plus K activated. Here, in general, now is a small k is just 1, or yes, because in axon just activate usually 1, but in reaction diffusion system it can be more. And N sites, if they come together close, they can coagulate or deactivate with some probability. And if you consider such systems for M greater than 1, the models exhibit first order phase transitions. And but this is true really in the high dimension mean field limit. And if you go below, you can find a lot of interesting things, which I tried to summarize in my book some years ago, which I am just advertising here. So what are the main points? In low dimensional regular Euclidean lattices, it is known that even these models exhibit critical point belonging to the directed percolation universality class at some lambda c critical value. So here, okay, the control parameter can be denoted sigma or lambda. When you tune at the lambda c, the rho can change from 0 absorbing state to some finite value with some singularity denoted by beta, as in magnetic systems, for example, with magnetization. But what happens if in such system there are heterogeneities? To be precise, quenched disorder, because if we consider the model homogeneous, this heterogeneities is just a disorder. So this disorder rounds the phase transition, and in between the inactive and active phase, there will be this active, extended region, the so-called Griffiths phase, which are caused by the rare regions shown here by a spin model, a picture here. So you can see these regions which are more coupled somehow to each other. And I will show it in a bit more detail, this rare region theory for quench disordered contact process, which is also belonging to this directed percolation universality class. So if you have a clean model, you can have a phase transition in this contact process at lambda C0, which is called the clean critical point between the active and absorbing state. But if in the system there are these heterogeneities or disorder, there can be these regions which can stay locally active even if the whole system has already flipped to another state, for example, to inactive state, and they can follow the transition of the whole very, very slowly due to these inhomogeneities. Let's parameterize the probability of these real regions of size LR with an exponential distribution with some C control parameter. And it turns out that if you go into this inactive phase, they would give the main contribution of the total rho. So this convolution integral here is just an expectation value of the rho, where LR is the size of the region, W is the probability of the occurrence of these real regions, and there is an exponential time factor E ad minus t to the tau, where tau is the characteristic time of these real regions. So what happens in this system if you vary the lambda? If you are below, lambda is smaller than lambda C0, you can find conventional exponential fast decay in the system. But if you get into the critical point, the clean critical point, the tau will scale as expected in a finite critical system with the real region size and dynamical exponent z. So if you plug this tau into this convolutional integral and you perform, for example, a saddle point analysis, it turns out that the critical behavior will be stretched exponential. If you go a bit further into the active phase, the tau, the lifetime, will be an exponential of the size of the system. And if you plug this tau into the convolution integral, the rho will decay with a power law with continuously changing exponents. Here you see the exponent is a function of C and B. And at the dirty critical point, which will be the true critical point of these heterogeneous systems, you find that even the B diverges, and it causes logarithmic time dependencies, ln t to the minus alpha of rho. And this can be described by the so-called infinite randomness fixed point according to renormalization arguments. So at the point to be remembered is that in the Griffiths phase, you find dynamical criticality, and furthermore, all over the region, the susceptibility diverges. I will show some very recent results by us that Griffiths phase can even exist below first order phase transition. So if we just take this threshold model, which I just introduced before with this K threshold, you can set up a mean field equation for rho. So it is composed of two terms, an activation term, lambda times rho squared times 1 minus rho. You need empty sites to be activated, and the mu is for the activation. And if you choose this mu equal 1 minus lambda, you can solve this simple equation in the steady states for d rho divided d2 equals 0. And the solution is real and positive when lambda is larger than this lambda c value is 4/5. But it turns out that in finite, it occurs only in finite systems at finite lambda, because I omitted the details, but if you have a finite system of node number n, the true critical point will be this formula. And if you go with n to the infinite size limit, this lambda c will go to 0. So in the real systems, you don't really see this infinite systems. You don't see these transitions only at the lambda equal 0 point. But in the finite system, you always find it. And it turns out there will be a first order phase transition in this model. And rho c, so the rho doesn't go to 0, but there will be a 1/2. So rho minus rho c will disappear with this lambda minus lambda c 1/2. So there will be a critical like exponent, singularity exponent here. And the temporal behavior is also a power law. Rho minus rho c disappears linearly, 1/t minus 1. Okay, so this is for the mean field. But if you put in this system in a heterogeneous hierarchical modular network, which we have tried, I don't go into the details, it turns out by simulation that you will have a first order transition plus this Griffiths phase. So in the plot, you see the simulation results, rho as the function of time for different lambdas. For lambda high, the rho values saturate to some finite, but here there is a critical point. And in fact, there is a jump if you plot, because you cannot find a continuous singularity here. And in the inactive phase, you see on the log-log plot these straight lines corresponding to some dynamical criticality. So we found some numerical evidence of this coexistence of this so-called hybrid phase transition and Griffiths phase, and also multi-stability existing in these models. Okay, now let me turn to another direction about the connectomics. So what do we know about the structural networks? You have already heard many great talks about it. I just tried to summarize my knowledge. So the largest precisely export brains structural network is the C. elegans, which has about 300 neurons. And very recently, the fruit fly partial hemibrain is available, which has a node number of 22,000. So these are exactly known, more or less exact methods. But these systems for statistical physics simulations are too small. You may know it because simulation can suffer from finite size effects and rounding effects. And if you have rounding effects, it is very difficult to know that rounding is due to Griffiths phase or finite size effect. So therefore, we consider larger connectomes, which are not exact, but they were obtained by diffusion MRI measurements from pictures, which can contain about almost 1 million nodes and voxels. But these nodes are not neurons themselves, but each node is about 1 millimeter cube size of the brain. So it can contain already tens of thousands of neurons. There is a disadvantage that these connectomes have unknown faithfulness, and there is an intensive research is going on to automate image processing. But there was a very recent comparison which I have found, which showed that these DTI, MRI connectomes are not so bad if they were compared with some more exact methods. So these large connectomes were collected in the so-called Open Connectome project, which is unfortunately finished, but the repository is still there. And from here you can download images or graphs of humans and animals. And we have downloaded some of them some years ago. I showed the details. So these are 1 millimeter cube voxel resolution images. So they can have 100,000 to million nodes. They are hierarchical modular graphs. The top level consisted of 70 brain regions corresponding to the so-called desiccant atlas of the brain. And the lowest levels were determined by this deterministic tractography method with some algorithms, which I cannot explain. But the main point is that the voxels can be mapped onto vertices of graphs of 10 to the 7, the fibers to edges of a graph 10 to the 10 originally, and after some noise reductions, you can obtain these graphs which are undirected but weighted. And we performed some graph analysis first on some of these large human graphs we downloaded. These are denoted by, for example, here KKI21, which is corresponds this Kennedy-Kruger laboratory, some number. And first we were interested in about the degree distribution, because there were many papers that these graphs are scale-free. But in principle, already at the first look on this log-log plot, you can see they are not really straight lines on the tails, but simple fitting results in stretched exponential tails. But to be more precise, we applied a maximum likelihood fitting for the nodes supplied with the so-called AIC information theory model. So this means that you have parameters V for the nodes Ki, degrees Ki, and you measure this maximum likelihood number, but to compensate with the number of parameters, which is the capital K, there is this second term. So because if you have infinite number of parameters, of course, the fitting can be very precise. So there should be a compromise between the likelihood obtained and the number of parameters. So we determined these fitting parameters, and this method also resulted in the best model, the stretched exponential, with more or less universal exponents. But I will show a bit more detail, but another important point is that if you consider the weight distribution of these links, it turns out that they are more like power law, as can be seen on the second graph. So in this red dashed region, you can fit a power law with the exponent around -3 for this KKI 18 weights. And in the inset, you can just see the modular structure, which we also determined for this model. So here are some details of the graph degree analysis. We tried different models: exponential power law, log normal Weibull, truncated power law, and generalized Weibull. Here are the functions, and here are some examples of the fitting of the observation and different functions. And this we measure this AIC number, and delta J is just AIC measure with respect to the minimum value, which is plotted in this table for different connectomes. So you can see the different functions, and so you have the best results when this difference is the smallest, which have these bold numbers. When you have the smallest numbers of the distance from the minimum, and so this is the best for this generalized Weibull, which is and truncated power law also, which is this is the other name of the stretched exponential. So for this is generalized Weibull, here are the parameters of the functions alpha, beta, and gamma, and it turns out that the beta exponent seems to be it's hard to say it's constant, but the differences are not so high. So one may consider that one of these connectome can be used as a representative for further studies. And this is what we have done later on. And another important thing is the graph dimension of these connectomes, which we measured by the breadth search algorithm, starting from each vertex. So you start from each vertex spreading, a maximum spreading, and you measure how many nodes are available within the distance R, and R is not the Euclidean distance, but this is the how many hoppings are needed to reach a point. So this is the graph distance. And on the main plot, you see the results for several graphs. they all start with some kind of a little power law, but they saturate very quickly, even before R equal 10 due to the finite sizes. But if you plot the logarithmic derivative, the local slopes defined it in the lower level, you see that these in the initial region, the slopes are slightly above 3, which is the three-dimensional Euclidean dimension, but less than 4. And the green dots just show you the results for comparison cube, 100 lattice cube, 100 linear size lattice cube results. So here you see the local exponent go to 3 strictly, and after the finite size cutoff, it goes down. So this is just for a comparison with the green ones. So it goes above the Connectome results of those. And we also considered whether these dimensions have any dependence of the node numbers with respect to the graph. We had the graphs node numbers between 300,000 and almost 1 million, and the KKI are the largest one, which I show you. There were some other ones. So there is a slight growth of the measured topological dimension. It's not very large dimension differences, but one may not think of going to infinity, because the graph seems to be completely scale-free. So we can assume that the dimension remains finite. Okay, so we cannot scale up to the 10 to the 11 vertex of a real brain. This was our argument. And we also tried to investigate the small worldness. So we determined the small world coefficients, which is defined as the ratio of the clustering coefficients and the average path lengths, and both of them are normalized by the corresponding random graphs. And here is the definition of the clustering coefficients. I think there were some introductory talks of graph theory, so I don't try to explain it. The clustering coefficients, we measure 2 types of clustering coefficients. C delta is the number of closed triplets divided by the number of connected triplets, and the average path lengths between nodes normalized by the number of nodes. And this for random graphs, there is an exact formula for it, which is shown here. And this table summarizes for the KKI graphs our measurements. So these are the number of nodes, the average degrees, the path lengths, the clustering coefficients, and finally the small world coefficients. We measure two types of small world coefficients. Both of them are very large numbers, as you can see, for each connectome. And they also have some size dependence, but I don't want to discuss it too much. The main point here is that although the graphs are finite dimensional, appear to be finite dimensional, they are small world-like, since the sigma, the coefficient, is larger than 1. And we have published these results, as I said, in 2015, claiming these graphs are finite dimensional, non-scale free, and more or less universal modular graphs. Okay. Now, the next point is about the dynamical simulation, which was performed on one of the selected graphs, this KK18 graph. As I said, due to this weak universality, we can use this, and this has the 800 and around 800,000 vertices and 80 million weighted but undirected edges, and here you can see the weight distribution, which has this power loss. The weights, by the way, means the number of fibers connecting two nodes here. So the average weight was 5, and if we started simulations of this threshold model, which I have shown you, first I tried to find a critical point by the so-called cluster spreading simulation. This means that you activate a single site and follow the growth of the activity. And there will be these growing clusters or avalanches. And you can measure by simulation the survival probability PT, which we know that at critical systems, non-equilibrium systems, it decays with the next t to the minus delta, where delta is a critical exponent of such experiments. But the inset shows that there were really not too much critical point in the original model. The decay of the PT is exponential or saturating, but you don't really see this power. It is more like a first order, or maybe it is a hybrid type. I didn't investigate it at that time. But instead of that, I decided, I arrived to the conclusion that you cannot find the critical behavior because there are these huge hubs due to the fat tail distribution of weights, which doesn't allow the small weighted nodes to act. They just follow the big hubs. Therefore, the transition will be discontinuous. And so no Griffiths phase or criticality were found at these simulations. Therefore, I introduced some normalization of the weights at the nodes. That means the weights of the incoming nodes is divided by the sum of the incoming nodes. And these so-called relative threshold models are known to exist in neuroscience, and this just provides some local homeostasis in the brain model, and we can expect it because you have inhibitory mechanisms in neural processes which can suppress the incoming excitation. So this can be considered, this normalization, as a homogenization of the system. And another trial was that even going further, you can flip some certain weights to the negative values in a quenched way at the beginning of the simulation, and you can mimic a little bit more some inhibitory links. So with this modification, it turns out that the dynamical simulation provided these results on the right-hand side. The survival probability decayed in a power loss continuously varying power laws. You can see for different control lambda new parameters in a rather wide region. So it suggests this is for the unidirectional original connectome. And I also checked what happens if 20% of the links are turned directional randomly. That means I just erased 20% of the links, but only in one direction. And interestingly, the results seems to be invariant, at least in a qualitative level. You still find these power law decays, and in the insets of the figure in the graphs, you can see the look. Let me go and just push something wrong button. So in the insets, you can see the local exponents as the function of 1 over t. So infinite time is just at the origin. So at the infinite time limit, these slopes or exponents seem to saturate to different values, or can show some finite slope, but a finite slope on this log linear representation means a logarithmic correction to power law, which is quite good in case of Griffiths phases. In Griffiths phases, this is really can be observed. This logarithmic corrections. Okay. So the conclusion is no qualitative difference, but this omission of changes provides robustness and provides more long links, because originally I just randomly removed the links, and there are much more short links. Okay, but what about the connection with the experiments? You can measure the avalanche size distributions in these simulations, and this plot shows the spatial temporal size S distribution for different control parameters near the critical point, just in order to compare with this mentioned electrode experiment results. And so at the critical point, they seem to decay with this exponent 1.36, which is a bit away from the mean field value, a bit smaller one. And you can also prove dynamical scaling in the inset, where I just made a scaling collapse for the distribution of these avalanches, scaled distributions for fixed t measurements and avalanche temporal sizes. You can make a nice scaling collapse, and this also provides some justification on numerical evidence for dynamical scaling. So scaling is close to the mean field value, a little bit below. What happens if you introduce those inhibitory links with probability 10 to 30%? And it turns out the Griffiths phase remains, and it is known in solid state physics, because these Griffiths phases are coming from solid state physics, and that there in spin glasses, where you can have negative weighted interactions. So here the Griffiths phase remains there, and similarly as before, you can determine the avalanche size distributions, PS, different control parameters, and the tau varies between 0.3 and 2. 2 is the mean field value. So these are close to the Finnish group experimental values, which I mentioned at the very beginning. And this was published in 2016 by myself in Physical Review E. And I also went further to prove robustness by the addition of a third state, refractive state. It is usually done in neural simulations. That means after the activation, the sites became in a refractive state for a certain amount of time. I selected just one time step, and they cannot activate back the neighbor immediately. And they cannot fall immediately back to inactive either. So there will be this will be a three-state model. But even with this modification, you see the avalanche size distribution in this model show this non-universal power loss, and which can be claimed to be Griffiths phase. And finally, one can ask if there is a time dependence in the model, because up to now we assumed that the graph is static or quasi-static as compared to the signal or the neural excitation. So, for example, the time dependence can be investigated by time-dependent thresholds of the model. And if you make these time-dependent thresholds, simulation shows that the Griffiths phase really shrinks, but survives for weak variations. And this is shown on the last plot below. Okay. Now I will turn towards the oscillatory models, because you can also take these graphs and investigate the oscillatory behaviors. As we know from previous talks and experiments, these neurons emit periodic signals, and one of the simplest models to describe the behavior of phase transition is this Kuramoto oscillator model introduced in 1975. On the top, you have these oscillators with angles theta I, and the interaction is just the difference of the thetas, the sign of the thetas, summed up for all connected graph points with this Wij connection matrix. So you have integrals, phases, and there is a global coupling in the Kuramoto model, which is the control parameter, and you have the weighted adjacency matrix. And in the model, you have these omega I zeros, which are the intrinsic frequencies of the oscillators. And this is usually chosen to be a Gaussian distribution. And to describe the phase synchronization, you measure the average phase, the Kuramoto order parameter shown here, which is non-zero if you are above Kc coupling strength, and tends to zero if you are below the Kc, as there is a finite size minimum for the fluctuations, because in finite system n node size finite system, there is a minimal fluctuation corresponding to this Gaussian fluctuation. So 1 over square root of n is the minimum of the Kuramoto order parameter. And at the critical point, you can find power law behavior. For example, if you start from an incoherent initial state, the R will grow with t to the eta exponent, you multiplied some scaling function, and here is the n is just size dependence. And these are known for mean field models, these results, but for non-mean field results, not too much known. An important point is that a real critical phase transition, a critical transition can only happen in if the dimension is larger than 4, the spatial dimension is larger than 4, which is a mean field graph. And this can be observed in full graphs, for example. But if you are tried to investigate it on other complex networks, as we have done in collaboration with Robert Weiss and Jeffrey Kelly, you see very ugly corrections to this mean field scaling and chaoticity, which is inherent in this model. So for example, if you take the Erdös-Rényi random graph and follow the de-synchronization, so if you start from a synchronized state and measure R for different control parameters, at the criticality, you don't really see nice power laws. And here this plot just shows you the effective exponent of these results. If unsynchronized, synchronized phase, and 1/2 is the mean field value where this effective exponent should extrapolate. So it is really very hard to see. There is a suggestion that there is a saturation to some other value here, but we did not go into the speculations. But this is an infinite dimensional system. Erdös-Rényi, we just claimed that this is a mean field with this extraordinarily strong correction to scaling. But inside of the decay simulations, if you start from a single, from an incoherent state, you can see better power laws. So this shows the results for two-dimensional lattices of linear size 6000, where you have periodic boundary conditions and extra long links as the fifth link between the nodes. So altogether, these are these so-called generalized small world network. You can control the topological dimension with the long links. For this model, you have 90,000 edges. And if you start from the random initial state and follow the evolution up to 1,000 steps, you can see a quite nice power laws, which is also exemplified by the effective exponent. Effective exponent eta seems to go to around 0.6 or maybe 0.7. Here I technically just say it is not trivial. You have to make an average over 10,000 independent realization of omegas. So the method is a deterministic Runge-Kutta method. We still have a probabilistic part which is coming from this quenched heterogeneity of the omegas. So the critical point located in this model and the critical exponent read off. And now I went further, or we went further a little bit to determine the avalanche exponents. So how do you define avalanches? This is not a trivial thing. In electrode experiment, they don't do it like this. my idea was just to get some characteristic time tau t, which measures the first return time if you start from a fully incoherent state. So these are the independent realizations of the order parameters, and return going to this lower threshold, which I mentioned is the square root of 1 over n, is this dashed line. When the measurements hit or first cross the values, you can measure some characteristic times, like in statistical physics, and you do many realizations in model. You can perform histogrammic, and you obtain these distributions of these return times. And now you can see some power law tails at the critical point with a tau t exponent 1.6, which could be obtained by fitting. So in fact, yeah, so just know that it is, I think it was in a finite dimensional system, and it's not a real phase transition, but a crossover, but you still can see almost like a phase transition. I mean, the main difference is the critical point can vary with the system size in crossover points. And in the Kuramoto solution of this graph, you also find these crossovers because the graph dimension is less than 4, as I said. And so if you do the method, which I just did for the 2-dimensional case, you can locate a synchronization transition point with the inflection by observing the inflection of these curves. So you start from an incoherent state, you follow R, and some of the graphs as a convex, some of them concave structure shape, and around the blue line there is the transition point. By the way, in the lowest level, you can see also the steady state values as the function of the control parameter. And so you see a very, very smooth crossover from incoherent to coherent in this system. So there is no real phase transition, but this transition, and after this normalization applied, I told you, you can get the transition, let's say Kc point with the growth exponent 0.6. And going to the Avalanche distributions method, which I just sketched before, I also determined these crossing times in case of this KKI-18 graph. And you can see on the graph right below the critical point, which is at 1.7, you see some power law tails, non-universal power law tails. At the critical exponent, the tau2 is 1.2, which is much smaller than the mean field value. But if you are below the critical point, the tau exponents vary between 1.5 and 2.4 in agreement with this experiment of long-range autocorrelations by these Finnish groups. And also this was done just to prove robustness by flipping the weights randomly, 20% of the links, and qualitatively you find the same behavior. In fact, we don't really claim Griffiths phase here, but it's another name, maybe Ginestra mentioned yesterday. They called it frustrated synchronization because there are these domains which locally remains synchronized for a long time, but it is, I think it is very similar to Griffiths phases. Okay. Okay. We have also studied to flip all the links of a node, incoming link weights 5%, which is a bit more like an inhibitory node. Or no, sorry, this is outgoing weight. So you select nodes randomly, 5% of them, and flip all of their outgoing weights. So these are considered to these inhibitory nodes. And after performing this analysis, this characteristic time exponents tau tail remains within this range of experimental values subcritically. And finally, we try to make this model a little bit more realistic. So first, just observe that this Kuramoto equation has some invariances with respect to the omega I distribution. It is well known. It has a we will use it. So the importance of this, that omega I in brain experiments should be greater than 0, because neurons are not really oscillators which can have a negative angular velocity. So omega I should be greater than 0, and distributions by experiments are lie in a very narrow region. So the sigma is 0.02 in experiments, and we used sigma equal 1 simple Gaussian ones in the previous slides. And mean value is also very slow. It's about 0.05. But the mean value can be gauged out by a rotating coordinate system in the Kuramoto equations. And also a rescaling can be done on the equations. So if you rescale the omegas by 8 times omega, you can get the same results if you rescale the time and the global couplings. So the main conclusions that our results, which I have shown you, can be transformed to those brain experimental results for later times and to weaker couplings. Okay. We also investigated what happens that if you have an annealed noise, an extra term in the Kuramoto, a time dependence noise. And it turns out that for the distributions of the avalanche sizes, it had no observable effect, at least for weak, sufficiently weak noises. So let me go to the conclusions of these investigations. Heterogeneity effects and scaling laws can be investigated on large connectomes and random small world graphs. This is what we have done to do a real statistical physics analysis, because otherwise, in small systems, these effects of roundings and finite sizes prohibit to see real scaling behavior. These graphs, which we downloaded from this Open Connectome project, were shown some degree distribution universality, a stretched exponential, as I told you, finite dimensionality and small world mass. And if you make the model homostatic one with this relative thresholding or renormalization of weight, you can find the occurrence of dynamical critical behavior like in Griffiths phases. In case of the fluctuation model, we can show that the mean field dynamical scaling occurs if you assume very, very ugly corrections. I mean, it was really beyond the computational possibility of justifying the type of corrections. We advanced a new method for measuring this characteristic time, which is assumed to be valid even in case of crossover for these synchronization transitions. And below the transition point, in these models, where there were strong heterogeneities, non-universal scaling of synchronization could be found. The duration exponents are in agreement with the LRTC experiment for humans, and we have shown the robustness, for example, by introducing further disorder by inhibitory links or inhibitory nodes. We have also shown invariance with respect to the frequency, some frequency distributions, and some insensitivity for weak Gaussian noise. And we have just published a review, which is on the archive at the moment. I think the number cannot be seen very clearly, but I would like to thank my collaborators, Jeffrey Kelling from the HCDR Institute Dresden, Gustavo Deco from the University of Pompeu Fabra Barcelona, and Michael Gessner, who was a postdoc by us, but now who is working in Singapore. So thank you for your attention.